let's see now, if it's irreducible, I believe it has only one. Oh, no, here, this is true even if there's a whole hyperplane of stationary distributions. So you approach every point on that hyperplane monotonically. Yes, that's a good point. This is true even when mu isn't unique. This monotonicity is true even when the stationary distribution mu is not unique. But the convergence to zero depends on the uniqueness of mu. Now we'll have one further application of this. Further application. Let P be doubly stochastic. Row sums equal 1. That means it's stochastic. You've got to go somewhere from any given state. But the column sums are equal to 1. And there are many doubly stochastic matrices, and it turns out if a matrix is doubly stochastic, then mu of I is 1 over m for all I. I equals 1, 2 through m, the number of states in the process. You could just see that you could verify it. It takes 2 lines to verify it. That if P is doubly stochastic, then the stationary distribution is uniform. And nicely, it is also true that if the stationary distribution is uniform, then the matrix is doubly stochastic. Well, in this case, then d mu n, the distance between your distribution at time n, and mu, well, this is mu of I equals 1 over m, is equal to summation of mu n of I log mu n of I over 1 over m, because that's what mu I is. So the distance from mu to the stationary distribution for doubly stochastic processes is this, which you'll see, this is just, these are non-negative sum to 1, this is log m minus the entropy of the distribution mu n. Well, this is what we call h of x sub n, the entropy of the state at time n. So now we see if d decreases, that means h increases. And if d decreases to 0, that means h increases to log m, and therefore we have h of xn converges monotonically to max h, that is, to log m, and this is true for all doubly stochastic Markov chains. But you'll notice this is a second law type statement. It says the entropy increases. Look, I put the gas in the corner of the room, it spreads out. The stationary distribution is the uniform distribution of position of each gas molecule in the room. So the entropy of the distribution of the gas increases to the maximum entropy distribution. Now this is true, remember, only for doubly stochastic processes, or equivalently, it's true only for processes for which the stationary distribution is uniform. So if mu equals uniform, now, what's the relationship of this to what we proved before? Well, before we weren't real happy because we were talking about stationary processes, and the entropy of the stationary process stays constant. So we looked at conditional entropies as what we probably mean. But in the case where the stationary distribution is uniform, we can start in a non-equilibrium state and state that we will monotonically increase the entropy until we hit the maximum. We don't need a conditioning, h of xn given xn minus 1, as these summary statements were. We could throw that away, and all that's needed is that the stationary distribution be uniform. Here's something I bet you haven't noticed. Suppose somebody says, oh, here's an M-state Markov chain. And the distribution of the state at this time is mu tilde. And it's not the stationary distribution. So you say, oh, well, I guess this process has been going on a long time and it hasn't reached equilibrium. Well, you can make a sharper statement than that. You can say, this process started at most 6 units ago of time, or 7 units ago, or so on. Here's the argument there. We'll make it very informal. Here is the possible distributions at time 0. After one action of the Markov chain, this vertex goes to here, this vertex goes to here, and this vertex goes to, say, here. So any mixture of the vertices, convex combination of the vertices, goes to this inner triangle. And then this further on, this gets going to this little triangle, and so on. You just follow the extreme distributions. Say, this would correspond to starting in state I with probability 1, where it's the ith vertex. Great. So, when somebody says, oh, mu is here, mu tilde. I'm starting in this distribution. You say, well, it couldn't have been going on for 2 units of time because it's outside the set of all distributions that you would get in 2 units of time. It could have been going 1 unit of time or no units of time. So if you're not in equilibrium, you have a finite history about how your distribution could have arisen through Markov actions. Question? Again, a little louder. It's the line station. I still didn't quite hear that.
The lines between the vertices, do they stay straight?
Yes, they do. Yeah. It's these are linear transformations of the vector mu. Yes, the lines stay straight. So you map one simplex, which is the general triangle, into another simplex, and so on and so forth. And I believe each of these is in the previous one. Yes. Yeah. Oh, and by the way, what's the limit of this process? It's mu. That is, these shrink down to a sequence of triangles converging to mu itself. Okay, so now we do have a second law statement that talks about the entropy itself. And so a lot of the statements of the second law in physics are where implicitly the maximum entropy distribution is uniform, the stationary distribution is uniform. All right, great. Let's take a 2-minute break. When we come back, we'll do Kelly gambling and optimal gambling. Okay, I'm picking up the homework set, whatever it is, here, and you can also put them in the bin, but they have to be in today. Yeah. What?
I can't quite get why there's a 0 here.
Here's why. Because if you look at the conditional distribution of P of y given x here, it's P of y given x, the Markov one. If you look at the conditional distribution of Q of y given x, it's again P of y given x because it's Markov. Yeah. You say, aha, why then isn't this equal to 0? In fact, I'll start the lecture by pointing that out.
This one is...
I don't think you need I. You just need T. Yeah, so TI1.
Right.
You're right.
Just because it's constant P going forward, Pij, doesn't mean it's constant P going backwards. It's still Markov, but yeah.
If and only if T, so if T is positive, then this matrix is something that if and only if.
All right.
That's your possible.
We're going to start again. Here's a fun little puzzle. As you look through this totally convincing proof that d mu, and the mu's get closer as time goes on. We expanded it 2 different ways and found this distance of 0 because the transition matrix is the same for the P process and the Q process. But then the question is, why isn't this term